Okay, we're continuing on here, chapter 11. So last time we got into electrons and electron configuration. So electron configuration is, again, pretty much the order at which electrons go into the atom, how they're filled into the atom. There is a certain order that they go in, and they do go into what we refer to as orbitals. And there are s orbitals, p orbitals, d orbitals, and f orbitals. We do have on every energy level s orbitals, and there's only one type of s orbital. On p orbitals, they begin on the second energy level, and there's three different types. And d orbitals are on the third energy level, and there are 5 different types. And on the fourth energy levels where we see the f orbitals come to light, and there's 7 different types. I guess I should do a 5 there. That means that each individual orbital could hold a maximum of 2 electrons, and that means you could put 2 electrons there, 6, 10, and 14, if you were to fill them all up. Remember that when you have a group of orbitals together, like a set of p orbitals, like the px, py, and pz orbital, they are sometimes referred to as a subshell or sublevel. And same thing with our d. So we talked about writing electron configuration. So if you know pretty much the maximum number of electrons that you could put into either a orbital or a subshell, you could also recreate the order at which they go in there pretty easily, like we talked about. You basically just need to remember those few things. That on the first energy level, that is where the S's start, and then the second energy level is where the P's start. Then the third energy level is where the D's start, and the fourth energy level is where the F's start. And again, at that point, you can basically just fill in the numbers, and you can recreate for yourself pretty easily the order at which electrons go into the atom by making this little chart here. And once again, we always start up on top, and again, we just zigzag back and forth. Remember that the place where a lot of people screw up is right around here. Again, the 4s is actually lower in energy than the D, 3D, and that follows for all of them. So they do get the electrons first. And again, you just keep kind of zigzagging back and forth until you put all your electrons in there. You get something like, 1s2, 2s2, 2p4, for example. And if we count up the top here, that is how many electrons. So that would be 8 electrons. And that would be our friend oxygen, I hope, is our electron configuration we're looking at here. This tells us the first number, again, is the principal quantum number, which is the energy level. So that is on the first energy level, n equals 1, has 2 electrons. On the second energy level here, n equals 2, it's got 6 total electrons, 2 in the s orbital and 4 in the p orbital. We also talked about drawing orbital diagrams, which is another way to represent electron configuration using either boxes or lines to represent the orbitals. So if we were to do our orbital diagram for this one, remember that the first electron in always goes in the upwards position, which means that it has a positive spin. The second one that goes in the opposite way, and that's what is referred to as being paired spin. Again, we go up and then down. Remember, when we have a subshell with a set of different orbitals, electrons go in one at a time first. So they do go in one at a time. And at that point, once they have kind of filled up one at a time, they will then go back and pair off. So that is the proper way, again, for them to go in. Couple of rules sort of govern how those electrons go in. Pauli's exclusion rule, which basically says no 2 electrons could have the same 4 quantum numbers. and Hund's rule, which is basically sort of the maximize the parallel spins, which is why, again, the electrons go in one at a time before they come back and sort of pair off. We also talked about transition metals and a couple of things that happen with those, and also when things gain charges. So when oxygen gains a charge, it ends up with 10 electrons. And that means that its electron configuration would be 1s2, 2s2, 2p6. That is also the same electron configuration as neon. And that's also a way that you can sort of shorthand some of this. So for example, if we had 1s2, 2s2, 2p6, 3s1, which would be 11 sodium's configuration. This part of it, which is 10, is neon. So you could put neon in brackets and then kind of continue on with a sort of a shorthand approach to writing electron configuration. What goes in the bracket always needs to be and then you obviously just continue on with its electron configuration. Remember that when transition metals, like we looked at iron, I think, which is basically argon 4s2 3d6. When you look at the configuration for it, when it loses electrons, say like +2, transition metals will always lose those s electrons first because they actually end up being higher in energy once electrons go into the atom and start filling up that d orbitals. So transition metals are a little bit different than representative metals. They will always lose their d electrons first because as the electrons go in, they do fill up the s first and then the d, but there is a switch in energy that sort of occurs once they start populating the d orbitals. So when they do lose them, they will lose those s1s always first. And then if they need more, they will delve into the d's to sort of finish out whatever remaining they need. So I think we also looked at iron with a +3 charge. And that would be argon 3d5, as it would lose 2 from here and then 1 more out of the d at that point. Any questions on electron configuration, orbital diagram? As you could also see, transition metals do not end up back at the noble gas configuration, as they have a little long way to go to get there. Any questions on that? All right, so I think where we left off was right around here. So we're gonna finish up talking a little bit about some trends on the periodic table, which some of which we talked about earlier on, but officially here we'll talk about it. So valence electrons are the electrons in the outermost or highest energy level of an atom. They are in the important electrons as they're not held as tightly, and they are also the ones that are involved in bonding. So as we talked about when we did bonding, these are really are electrons that are involved in bonding. When we look at nitrogen's configuration here, 1s2, 2s2, 2p3, we have 2 electrons in the lower energy level, and we have 5 electrons in the higher energy level, which would be the second in this case. So something like nitrogen has 5 valence electrons. Now, if we look at something like, say, sodium, which we had a second ago, 1s2, 2s2, 2p6, 3s1. This are all lower energy. These are higher energy levels. So here would be its 1 valence electron here. Sometimes our lower energy electrons are what are referred to as core electrons. And core electrons are the ones that are closer to the nucleus. They're held a lot tighter and they're not involved in bonding. So when we do bonding, it's just those high valence electrons, higher energy level valence electrons. Really, the easiest way in a lot of cases to figure out the valence electrons, as we talked about when we did bonding, is the valence electron should equal the group number on the periodic table. So again, if we look at nitrogen is group 5 on the periodic table, so it has 5 valence electrons. If we look at sodium as group 1, it has 1 valence electron. So that's a lot of times easier than just writing the electron configuration. It's just to look at the group number, and that will tell you how many valence electrons something should have. And as we see here in these examples, fluorine group 7 has 7, fluorine also group 7 has 7, and carbon group 4 has 4. And again, carbon 1s2, 2s2, 2p2. And it would be these 4 right here is the valence electrons for carbon. Questions on valence electrons there. So let's talk a little bit about some of these periodic trends. As we saw, as you go down a group, especially in a metal, they do give up their electrons a lot easier. So in order, if we look at group 1 there, cesium, which is towards the bottom, will let go of their electrons a lot easier than lithium will. We also saw this in terms of activity when we did that experiment way back when. It was increasing in reaction activity there as we went down that group. I think we saw that video again, lithium, sodium, potassium, and again, it increased in terms of its reactivity as we kept going down that group. Opposite of that, as we also saw when we did that sort of halogen single replacement reactions, when we had the different layers, we saw that in terms of group 7. As you went up the group, iodine was less reactive than bromine. Bromine was more reactive than iodine, and chlorine, and then fluorine. So when we talk about metals and non-metals, some of these periodic trends explain why we see sort of our most reactive spots at the extremes of the periodic table, because they basically have these periodic trends working to allow them either lose electrons in terms of metals or really gain electrons in terms of non-metals, which will make them quite reactive. So one of the important aspects of that is what is sometimes referred to as effective nuclear charge. So Z effective, which is effective nuclear charge, is sort of the strength of the positive charge from the nucleus that an electron fills. So for example, if we look at lithium, which is 1s2, 2s1, lithium basically has a +3 nucleus sort of charge, and it has basically 2 electrons. I'll just draw them kind of near each other on that first energy level. And it's got a further electron on the second energy level away from the nucleus. So when we think about sort of how these electrons are going to be held and how tightly they're going to be held, effective nuclear charge is important as it explains why certain electrons are held tighter than others. When we talk about the attractive force here, which is the electrostatic attraction, is basically the positive negative attraction between the different charges. In this case, the negatively charged electron and the positively charged nucleus. That electrostatic attraction between positive and negative gets stronger with the charge of it. So again, something of a larger positive charge will hold something tighter than something with a smaller positive charge. So +3, -3 will be held tighter than, say, +1 and -1. So when we look at our lower sort of core electrons here, these are our core electrons. These guys are pretty much feeling the full brunt of that +3 charge from the nucleus. So they're going to be held really, really tightly. Now, when we get to our valence electron out here, which is a little further away, our valence electron is actually experiencing what is sometimes referred to as shielding. And it is experiencing shielding from the lower energy level electrons. They're like in the way, basically, is the idea there. So instead of feeling that full +3 charge from the nucleus like those core electrons are feeling, it's actually feeling something a little bit different. And that's because those guys are sort of in the way. So you could think of shielding as, you know, when you sit down like in a movie theater and you got nice seats and somebody comes in and obviously sits down with a big giant hat in front of you, kind of shields a lot of the screen. And that's sort of the same idea here that happens. Now, because this electron is feeling shielding, we could calculate the effective nuclear charge it's feeling by taking the charge on the atomic number, basically, which is +3, and we could add it to the number of electrons that are basically shielding it. And what we see here is, effectively speaking, instead of that outer electron filling a +3 charge attraction, it's actually only feeling like a +1 charge, which means it's not going to be held as tightly as those core electrons. And it's going to be much, much easier for that electron to be lost. And that is why valence electrons here are what is involved in bonding, because they're not held as tightly because of this effective nuclear charge. They're not going to be held tightly and easier to remove or be shared. When we look, generally speaking, on effective nuclear charge, it increases as you go up and to the right and decreases on the periodic table as you go down. As you go to the right on the periodic table, things have more protons, right? Which means they have more protons in their nucleus, creating a much larger positive charge in the nucleus, which is going to bring even the outer electrons in much closer, along with those core electrons. Any questions on that? So effective nuclear charge explains why certain electrons, which are valence electrons, can sort of be removed and used in bonding, because, again, they're not feeling that full brunt of that positive charge of the nucleus. Any questions on that? So let's talk about what happens when somebody does sort of lose an electron. Ionization energy is the ability of or is the energy required to remove an electron from an atom in the gas phase. And that's what happens when we do lose it. Metals have relatively low ionization energies, and nonmetals have relatively high ionization energies. And electrons actually do come off basically one at a time. So things do not lose all their electrons at once. They actually come off in sort of a stepwise fashion. And when we look at the periodic table and we think about ionization energies, we associate ionization energies with, the formation of cations. Those are basically the things that lose electrons, right? And when they lose electrons, they become positively charged. So the charge associated with it is related to how many electrons come off. And when we look on the periodic table, as you go up and to the right, it increases. As you go down and to the left, it decreases. Now, because electrons do come off one at a time, there is an ionization energy for each of those steps. So, for example, magnesium, the first thing that would happen is magnesium would lose one electron. And that is what is sometimes referred to as the first ionization energy. Then what would happen is this magnesium with a +1 charge would lose another electron. And that is what is referred to as the second ionization energy. And then perhaps this guy will lose a third electron. And that would be the third ionization energy. So in general, the general trend of first ionization energy is it increases as you go to the right and up, decreases as you go down. It also increases as you go from the first ionization energy to the second to the third, as it takes a lot more energy to remove electrons after you have already removed one. So if you think about what happens from here to here, after you remove that first electron, the overall size of it gets smaller, right? Because it lost some electron cloud. Now you have even those outer electrons that have now moved closer to the nucleus. So they're going to feel more of that positive charge. And now what happens is it takes a lot more energy to remove the second electron. It gets smaller after you remove the second electron as it loses another electron. So again, it just kind of keeps shrinking and moving those electrons closer to the nucleus, which means they're going to be held tighter. So as we go from, say, first to second to third ionization energy, it increases a lot. So at some point, it really, really jumps a lot as you go into a certain spot of it. Question on that there. And here's a table of some ionization energy, and it shows our trend. So for example, if we look at magnesium, to lose the first electron, it's about 735 kilojoules. To lose the second electron, it pretty much doubles. It's about 1400, so it gets much, much harder to remove that second electron. And then if you look and you want to try to remove that third electron, that's like almost like a 6 to 7-fold jump in energy, and it doesn't happen. And it doesn't happen because when we get to that third electron here, if we look at the electron configuration for magnesium, looks something like this. Magnesium has 2 valence electrons, which is pretty much through our first and second ionization energy. At that point, when you try to rip off the third one, you're now into its core electrons, which is really, really close to the nucleus. And under normal conditions, not going to happen. So that's why when we think about magnesium, it makes a +2 charge because easier to remove those valence electrons, but super hard at that point to try to rip apart energy-wise the third electron, fourth electron. That's also why if you look at sodium, when we think of sodium, which is group 1, usually makes a +1 charge because it only can lose 1 electron. And that's because it has only 1 electron, which is this guy. And once we lose that electron, you're looking at a 10-fold jump in energy to try to remove a core electron, and it just doesn't happen. So that's why there are certain things that have fixed charges. Because of this, as you get into those core electrons, too hard in terms of energy wise for those electrons to be removed. Any questions on that there? So let's talk a little bit about electron affinity. Electron affinity is the energy change that occurs when an atom gains an electron. So we think of this with anions, which are negatively charged. And as we go across a period, it increases generally and decreases as you go down. It's not a perfect trend as you go up and to the right, but that is the general trend. So for example, if you looked at the electron affinity for group 7, as you go up group 7, it would increase. And then when you get to fluorine, it'll actually come back down a little bit. So there is a little bit of a not perfect pattern, but the general pattern is electron affinity increases as you go up to the right and decreases as you go down to the left. And affinity means that you like electrons, so you're more apt to gain electrons as you go up and to the right on the periodic table. A reminder that when we talk about electron affinity, that is different than talking about electronegativity, which is the ability of atom to bring electrons towards itself. That also, in terms of the periodic table, increases as you go up and to the right, decreases as you go down, with fluorine being the most electronegative atom that you could have on the periodic table. So electronegativity is that ability to bring electrons towards itself. Electron affinity is actually the energy change that occurs when somebody does gain an electron. So they are different things, but very similar in terms of the outcome. As you go up and to the right, we're going to see things gain electrons. Any questions on electron affinity there? So all these sort of periodic trends also lead to what we see in terms of atomic radius. As we go up and to the right on this periodic table, the size gets smaller. As we go down and to the left, it gets larger in terms of the atomic radius. So these things do make sense if we think about sort of our trends. As you go up and to the right, you have things that have very high ionization energy, very high electron affinity and electronegativity, and has high effective charge. All of those things are things that basically mean they want to hang on to their electrons, they want to gain other people's electrons, and they're not going to get rid of their electrons very easily. are why we think about nonmetals, pretty much the ones that will gain electrons. As we sort of go the opposite way, so as we go this way, we have high electron affinity, we have high electronegativity, we have high ionization energy, we have a small size. So again, these are guys who are going to want to gain electrons because of that. As we go down into the right, or down into the left on the periodic table, we have pretty much all the opposite. They have low electron affinity, they have low electronegativity, they have low ionization energy, they are much larger. So all of those things account for why we see these guys typically will lose electrons. They really are not looking to gain electrons. They're not looking to hang on to the electrons they have. If you want them to lose electrons, it doesn't take a lot of energy to do so. And they are further away from the nucleus because they have a smaller effective nuclear charge, which means they're not going to be bringing those electrons in much closer, so they're easier to remove. Any questions on that? We also talked about there, again, when an atom loses electrons, it does get smaller in terms of its cation. When it gains electrons, the opposite is true. It gains electrons, so the anion is larger than the neutral atom because it is gaining electrons. Any questions on those periodic trends there? All right, so which should be the larger atom between sodium and chlorine? If we look on the periodic table, they are in the same period, and we see chlorine further to the right, which means it has higher electronegativity, higher electron affinity, higher ionization energy, and higher effective nuclear charge, which means it's going to drag all its electrons much, much closer to the nucleus than sodium would, which is further to the left. So sodium here should be our larger atom. Any questions on that there? Which should be the larger atom here, which is between lithium and cesium. And if we look at lithium and cesium on the periodic table, they are in the same group. Here we see cesium is further down, which means, again, it has a lower ionization energy, lower electron affinity, lower the effective or nuclear charge, which means it should be our cesium here, which should be a larger atom of the two. All right, which one is larger, the hydrogen 1s orbital or the lithium 1s orbital? So why don't you take a moment and think about it. So in this case, it's going to actually be the hydrogen 1s orbital. Now you may be saying they're both 1s orbitals, so shouldn't they kind of be the same? The difference is what we have in the nucleus, right? So if we have hydrogen versus lithium, lithium has a +3, hydrogen has a +1, right? Total charge. So when you have your 1s orbital, this attraction to the nucleus is going to be stronger because it's +3 versus +1 attraction. And that's going to pull this 1s orbital in a little bit, which means the overall size of this guy is going to be smaller than what we have from the attractive force to the 1s orbital there in the +1. So that is why hydrogen is actually going to be larger. Question on that there. Which one is lower in energy? So this would be the opposite answer. Because of the 1s being dragged in closer to the nucleus, energy-wise is going to be closer to the nucleus and lower in energy than the 1s orbital that we have in hydrogen in this case. Any questions on those two there? All right, so we want to arrange these elements in increasing ionization energy. So that's sulfur, oxygen, and fluorine. So if we look at the periodic table here, oxygen, sulfur, and fluorine. So ionization energy increases as we go this way and up. And that means that the order is exactly what we see here. It should be sulfur, oxygen, and then fluorine. And in terms of atomic size, we want increasing atomic size. So the smallest atomic size, it gets smaller as you go this way. That means we want increasing, we actually want to go this way, would give us our increasing atomic size, with sulfur being the largest in that case. Any question on these periodic trends and why we see what happens with metals and non-metals? Okay, that wraps up this chapter. Okay, sorry about that. All right, so off to chapter 16 here, which is acid and bases. Second to last chapter, so that can't be bad. So let's talk a little bit about acids and bases. Acids were first recognized by their sour taste. Example, things like acetic acid is the major component there. Vinegar, we did some titrations, I think, with it the other day. Citric acid and lemons. Bases have a very bitter taste and feel very slippery. A lot of soaps, drain cleaners, those type of things are bases, as we might have talked about. When we talk about something being basic, is sometimes referred to as being alkaline, and that really means basic. And if you think about on our periodic table there, group 1 and group 2, that is the alkali metals, and that is the alkaline earth metals. And a lot of our bases, especially a lot of our strong bases, come from group 1 and group 2 on the periodic table, like sodium hydroxide, potassium hydroxide, calcium hydroxide. So a lot of group 1, group 2 on the periodic table, kind of hooked up with hydroxide, is where a lot of our strong bases come from. Really, a lot of our acids come from really oxides of nonmetals together and water coming together, like CO2 and H2O, makes carbonic acid, NO2, and some water will make some nitric acid. So a lot of our, when we look at the periodic table, where a lot of our acids and bases sort of come from, a lot of our bases come from here on the periodic table. And a lot of our acids really originate, upper right non-metal sort of region of the periodic table. Is where a lot of them are sort of come from. So let's talk a little about sort of the first sort of definition of an acid and base. And that was one done by Arrhenius. He did a lot of work with electrolytes. And if you remember, electrolytes are things that when they do break apart in solution, they produce ions. And those ions is what helps conduct electricity. He defined an acid as something that has the ability to produce hydrogen ions in solution. And when we talk about that, we're talking about the ability to, in solution, produce free H+. So these H+ ions are floating around freely in the solution. They're not attached to anything. So the ability of something to do that, to produce that in solution, is really important. It's also important when we talk about acid and bases is the idea that H+, which is the hydrogen ion, and H3O+, which is the hydronium ion, is essentially the same thing. So they're used interchangeable in equations and also formulas as well. I personally use H+ most of the time, but a lot of books and things will use H3O+. So almost anywhere I put H+ in this chapter, in a formula or even in an equation, you could basically substitute it for H3O+. So they're basically the same thing. They really mean the acid part of the solution. So H+, H3O+, kind of interchangeable in acid-base chemistry. In addition, H+, as we will see shortly, is sometimes referred to as a proton. And a proton is because hydrogen has one proton and one electron. Hydrogen does not have any neutrons. So in order for it to become positively charged, it has to lose an electron, which means the only thing it has left is a proton. So also in acid-base chemistry, when you see H+, people refer to it as a proton because of that. So those are kind of three terminologies or terms that are sometimes used to all describe really the same thing, an acid in solution. So when we talk about an acid, it is the ability to produce H+ or H3O+, however you want to look at it, freely floating around in that solution. A base, on the other hand, is something that has the ability to produce hydroxide or OH minus in solution. And once again, we're talking about the ability to release basically OH minus or produce OH minus in that solution and have a bunch of OH minus basically floating around. As we'll talk about in this chapter, basically the ratio of H plus to OH minus that you have in the solution is what's going to determine, is it sort of an acidic solution, basic solution, or even a neutral solution, is sort of the ratio of those things that you have freely floating in the solution. Once again, not attached to anything, kind of freely moving around in the solution part. Any questions on that there? So if we take some hydrogen chloride gas and we dissolve it in water, we will get H plus and Cl minus, and that will make us our acid, which is hydrochloric acid, right? So a reminder that if the acid does not have oxygen in its formula, we name it with hydro to begin with and ic. So this is hydrochloric acid. Also a reminder that if it does have oxygen in it, it will either have a polyatomic ion that ends in 8 or ite, like we talked about when we did naming. And if it ends in 8, it will be ic acid, like nitric acid. And if it's ite, it will be OUS acid, like nitrous acid. So a reminder in terms of naming acids, that is hydrochloric acid. Again, hydro and ic because no oxygen, as opposed to HNO3. That is nitrate, which means this is nitric acid. Ic acid, or HNO2. That is nitrite. And that means that this is nitrous acid, OUS acid. A reminder that, again, hydro is only for ones with no oxygen. So those are the only ones that have it. The other reminder as well is we typically put aqueous next to acids, as it means it's in a solution and it's able to release that H plus, and that's what makes it hydrochloric acid versus hydrogen chloride gas. Same thing with our sodium hydroxide. If we dissolve it in water, the ability of the HCl to release that H plus and the sodium hydroxide to release that OH minus is what makes each of these an acid and base. As we will see, not all bases, for example, have hydroxide in them. A lot of strong bases have hydroxide in the actual formula, but there are things like ammonia, for example, that can produce hydroxide and still considered a base. But definitely if you see hydroxide in it, it's probably going to be fairly strong base. Not always, but most of the cases it will be. Now, the Arrhenius sort of concept of acid and bases was a good sort of step forward. It was limited because he only really worked with sort of bases that had hydroxide in it. And as I mentioned before, not all bases will have hydroxide in it. So again, something like ammonia here is actually a weak base, because when it reacts with water, it will actually accept an H plus over there and make NH4 plus and OH minus. So unlike sodium hydroxide, which can basically just go for a swim and produce hydroxide, something like ammonia there needs to actually do a little bit of work to do that. And that's why this guy is a strong acid, a strong base, I'm sorry. Because it really is a strong electrolyte. Ammonia is a weak electrolyte. And again, if you remember electrolyte conversation, strong electrolyte will 100% break apart in solution. None of it will stay together. So as soon as sodium hydroxide goes for a swim, it's going to completely break apart. And it's going to produce a lot of hydroxide in that solution really quickly, because all it has to do is go in. Something like ammonia needs to go find some water, do a little bit of reaction to produce that hydroxide, so it's not going to produce as much as sodium hydroxide dropping in there. It will still be able to produce hydroxide, so it's still considered a base, and that's why it's a much weaker base than something like sodium hydroxide. Any questions on that there? So the next definition of an acid and base is one that most people sort of think about when they talk about acids and bases. And this is the Bronsted-Lowry definition of an acid and base. So the Bronsted-Lowry definition of an acid and base is an acid is a proton donor and a base is a proton acceptor. So the acid will give away the H+, the base will accept it. So for example, if we look at the reaction I just wrote up there, which is our NH3 plus our water, what happens here is the water will actually donate the H+ over, and we'll make NH4 plus and OH minus in this case. In this case, the NH3 would be our base, and water in this case would be acting as our acid, as it is the one that is actually donating the H+ over. Now, sort of the consequence of the Bronsted-Lowry definition of acid and base is when we have this reaction that occurs, it actually creates some partners on the other side. And if we look at it, the NH3 looks like it is related to the NH4 plus, and it is, and that is what is known as the conjugate acid. And if we look at the water, it is related to this guy over here, the OH minus, and that is what is referred to as the conjugate base in this case. So on one side of the reaction, when you have a Bronsted-Lowry, you have an acid. Its partner on the other side is what's referred to as this conjugate base. And if you have a base on the left-hand side, its partner on the other side is what's referred to as a conjugate acid. These are sometimes referred to as conjugate acid-base pairs. The only difference between the two is this 1H+. So this 1H+ that gets transferred is really the only difference between these two. And when we look between the base and the conjugate acid, it has one more H+ because it gained it. And when we look at the thing that's the acid to the conjugate base, it has one less H+, as it has lost it. And that should be the only difference between these two things. So the only difference between a acid and its conjugate base, or a base and its conjugate acid, is the 1H+ that was transferred. When you're looking for acid and bases, just run-of-the-mill acid and bases, that is going to be found on the left-hand side of the arrow. Your conjugate partners are typically found on the right-hand side of the arrow. So your conjugate acid, conjugate bases are typically found on the product side. Your regular acid and bases are found there on the reactive side. Yes, sir. H2O is the acid because it's actually the one giving away the H+ in this case to the NH3. And just to show you, for example, if we took HCl and H2O. In this case, this is going to be the acid. The acid here will actually donate the H+ to water. And in this reaction, the water actually will be accepting the H+, which means water will actually act in this reaction as the base. And you will produce H3O+ and Cl-. And once again, this acid, this would be its conjugate base. And this base, this would be its conjugate acid. And once again, the only difference is that 1H+. This also brings up a point that there are certain things like water, for example, that could act as either an acid or a base, depending on the situation. And those things are what are referred to as being amphoteric. And that is a substance that can act as an acid or a base. So there are certain things like water is an example that can do that. In this case, what will happen is, again, in the case of the one on the bottom there, the H plus, you can think of water as like H plus and OH minus. That H plus will come off there and attach to that ammonia in the case on the bottom. Any questions on that? This is also why, for example, that you can use H3O plus and H plus interchangeable. What's really happening here is actually just the strong acid going into water and breaking apart or dissociating. And this is a perfectly proper way to write the reaction, and probably the way that you would sort of see that reaction. But there's also a way sometimes that people write reactions for strong acids that does not include the water. And oops. So that same reaction where I did include the water. And again, this is really just showing this, which is a strong acid, just breaking apart in solution and producing H3O plus. You could also very easily, and it's very commonly represented because it's a strong acid, you could just write H plus and Cl minus. And these two are basically equations showing the same thing. And in this case, where I did include the water, I get H3O plus at the end. It's more of a Bronsted-Lowry sort of representation of what's happening. This is really, I don't say a shorthand, but really, kind of a shorthand of what's happening. That's just producing H plus. So those two equations are equivalent to each other. It's basically the same idea of just that hydrochloric acid going into the water and basically breaking apart completely. So if you do include the water in the reaction, you will get H3O plus at the end rather than H plus. If you exclude the water, which a lot of people will do with acids, showing it breaking apart, you will just get H plus, just that H plus sort of coming off. So they are equivalent, and why they're sort of used interchangeable. So that Bronsted-Lowry definition, again, will always create these acid-base conjugate pairs. This is a generic formula for an acid. So that's just like a generic formula. Remember that if it is an acid, the cation is always H plus, right? So that's always the positive guy in an acid. And the anion, obviously, to balance it out, you'll need maybe more than one H plus. So here's that example I just did. And again, we have our acid on this side. And in this case, once again, our water is actually acting as the base, as it's going to accept the H plus from the acid. And again, creating our conjugate acid and conjugate base. So when you're looking at, are these things acid conjugate base pairs or base conjugate acid pairs, that again has to be the only difference that there is, which is the 1H plus. It's also important to remember that it is not just a hydrogen that's being gained or lost, but it is the plus part of it, which means the charges of these things change. So when somebody loses an H plus, when they lose a positive, they become one more negative. So their charge changes on the other side. And when somebody gains, obviously, the positive, they become one more positive. So you do have to adjust the charge when you're doing the H plus sort of losing or gaining. And that's very commonly missed by people, the charge sort of aspect of it. And here's sort of what's happening in that acid reaction again here. That H here is the one that's going to come off and be donated to really a water that's swimming around in the solution and going to make that H3O plus, which is our hydronium ion. Just like if we looked at, say, nitric acid, if we drew the Lewis structure, by the way, again, for this guy here, which I think we might have did when we did Lewis structures, it is this hydrogen right here in this polar bond that is typically the one that will be lost when we lose nitric acid. That's the one that will basically come off to do that. And there's certain acids that can lose one hydrogen, which are referred to as being monoprotic. So a monoprotic acid There's diprotic acids that can lose 2 hydrogens, and there's triprotic acids that can lose 3 hydrogens. By the way, when something has the ability to lose 2 hydrogens or 3 hydrogens, as we'll talk about, they actually do come off one at a time. So they don't all really just drop off. They actually come off in a stepwise fashion, basically one at a time, until they have all basically been released into that solution. And by the way, generically speaking, sometimes people represent a monoprotic acid just as HA, like HCl is like a representation of that. H2A is sometimes a generic formula for a diprotic acid, like H2SO4, or like HCl, and H3A, like H3PO4 phosphoric acid, is a real life example of that. The difference between all those, the HA, the H2A, and the H3A, is actually the A part, the negative ion. The negative ion has a different charge. This is a +1 -1 charge. This is a +1 -2 charge. That is a +1 -3 charge, like phosphates -3, sulfates -2, and chloride is -1. So the negative part of that changes. And that's why you have more hydrogens, say, in the diprotic and the triprotic to balance out the charge, right? Because it's really like an ionic compound. You need to just make sure that it's balanced. Any questions on that there? All right, so take a moment here and decide which one. Okay, so let's take a look. So really the deal is the difference 1H plus is pretty much what we're looking for here. So if we look at the first one here, this combination, the only difference here is really just a 1H plus. You can put the H plus on the guy on the right, you get the guy on the left, or take off from the guy on the left, you get the guy on the right. So this one would be a pair. How about the second one here? Would this be a pair? The difference here is 1H plus, but it is also an oxygen, right? That one has it, the other one does not. So this would not be a pair because of that. Again, it can only be 1H plus difference, but because one has oxygen, one doesn't, it is not a pair. If we look at this guy here, the only difference here is an H plus. If I take off a hydrogen from the left, I have one left. And if I take off a positive, that means I become one more negative. So they do match on each side. So that would be a pair. And the difference here is also 1H plus. So that would be a pair as well. So it looks like 1, 3, and 4 would be pairs. Any questions on that there? All right, so why don't you try the next one here for each of these. For each of these, write the conjugate base for each of. Okay, so let's take a look. So once again, you should know that H plus should be the only difference. So the key here is, should you put it on? Should you take it off? That's the big question, I suppose. So this is where sort of understanding Bronsted-Lowry definition can help you. If you think about sort of what we had an acid plus a base, gives us a conjugate base plus a conjugate acid on the other side. So the acid on this side is related to the conjugate base on that side. The base on this side is related to the conjugate acid on this side. So in this particular case here, they want you to write the conjugate base. That means you want to end up with this guy, which means if you just follow it backwards, that means that everything you are looking at is an acid. And the definition of an acid is something that will donate the H plus. So that's how you know you should get rid of the H plus, kind of think about it backwards, because they will not always tell you, hey, these are all acids, or hey, these are all bases. They'll just say, hey, write the conjugate acid or conjugate base to this. So you kind of think about it backwards and just follow the definition. So following the definition, that means we're going to remove an H plus. So this will leave us with an H, an S, and a minus, as that thing was neutral to begin with. So it lost the positive charge. So it becomes one more negative. Then this guy would then lose a hydrogen, which leaves us an S. It has a -1 charge already, but it lost a plus as well. So it goes from -1 to -2 in this case, right? And again, that's what I was talking about earlier. You want to make sure you also adjust the charge as you write these things when it gains or loses. Here, it's going to lose a hydrogen. So NH2, once again, it was neutral, becomes one more negative. So it'll now be minus. And lastly, here loses a hydrogen and also becomes one more negative. So those guys there should be your conjugate bases to each of those acids in this case. Question on that there. So let's just say I had HCO3 minus, a little bicarbonate. What would be the conjugate acid? And what would be the conjugate base to this guy? So why don't you write the formula for each of those? Starting with that guy in each. Okay, so let's take a look. We'll start with the conjugate acid. So once again, if you're not sure, conjugate acid is here. If we go backwards and find its partner, that's basically a base. And definition of a Bronsted base is it will accept an H plus. So in this case, we're actually going to add an H plus to this guy, and that will give us H2CO3, gains the hydrogen, +1 -1 gives you no charge overall, makes a little carbonic acid. And just like we did in these examples here, we're looking for the conjugate base. So if we work backwards, that means that in that case, it would be a acid. So it's going to lose an H plus as we go that way, which will give us CO3 2 minus. Once again, becomes one more negative when it loses that hydrogen. Bicarbonate, also an example of an amphoteric substance, something that can act as an acid or base depending on the situation. A lot of times, if you have something with a hydrogen like that and a minus charge, they very often can kind of go both ways. It can act as an acid or a base because they have the hydrogen to give, and they also can receive it because they kind of have that negative charge. Something like, say, Cl minus can't do that because it doesn't have a hydrogen to give or anything like that. So it's got to have that hydrogen to be able to do that. Any questions on conjugate acid base pairs?